capacity for takeoffs and landings. In connection with a huge airport expansion, new engineering construction technologies are being employed. Among these technologies is the expanded polystyrene EPS construction method, which has been highly effective in combating weak soil conditions at a variety of construction sites. The EPS construction method, a lightweight ground stabilizing technique using expanded polystyrene, was developed in Norway. It is an ideal solution for stabilizing weak ground and as lightweight material for backfilling retaining walls. EPS foam block is also widely used to construct temporary roads and protection from falling rocks, to provide backfill for abutments and ground fill for parks, and to alleviate steep inclines and the dangers associated with landslide areas. The use of EPS foam in these civil engineering applications is being identified as geofoam. The main advantage of the EPS construction method is that it makes use of the extreme lightweight of expanded polystyrene. If you look closely at EPS, you will see that it is a collection of very tiny individual cells which are 98% air. The weight-to-volume ratio is phenomenal, about 1% the weight of sand. Although EPS is generally thought to be a soft material, it is pressure resistant, possessing the strength to resist loads exceeding 10 tons per square yard. Due to its unique cellular structure, EPS is resistant to extremely cold temperatures and water. Since polystyrene is hydrophobic, EPS foam has superb resistance to acid and alkaline chemicals, and its physical properties are ideally suited for geofoam stabilization and lightweight fill applications. There are two methods for manufacturing expanded polystyrene: the molded foam method, where blocks of foam are produced, and the extruded foam method, which produces sheets of foam. In the EPS construction method, very large lightweight molded foam blocks with excellent compressive strength and water-resistant properties are stacked upon each other as ground fill material. This technique is the most suitable method to stabilize weak ground, steep inclines, landslide, and other dangerous sites. In addition, no large transportation equipment is required, since block placement can be quickly performed by hand, making it a highly productive and economical construction technique. Here is how the geofoam technology was employed to handle weak ground conditions encountered at an expansion project at the Japanese National Highway No. 1 bypass. After excavation, the site is leveled and the sand is uniformly spread over the area which will receive the geofoam blocks. On top of the sand, a vapor barrier is placed, and the EPS foam is positioned so that there will be no voids between the blocks. Cutting of the foam is easily accomplished with the use of heated wires. Once the blocks have been placed, backfilling and earth compaction is carried out between the surrounding earth and the blocks. When more than 2 layers of blocks are laid, timber clips are attached to prevent slippage and movement of the blocks. After the blocks have been properly placed, steel reinforcing mesh is fitted on top of the blocks, and a 4-inch concrete slab is poured, both to protect the foam and to distribute the eventual load. After the concrete is cured, the roadbed is formed, and when the surface layer is paved, the job is finished. Project engineers report that through the use of the EPS construction method, there has been no further road settlement or need for further foundation repair, and overall, the project construction time is greatly reduced compared to the use of conventional technology. In the 1980s, when the EPS construction method was introduced into Japan, large-scale testing was undertaken by government and industry to study and confirm the reliability and safety of the technology, the result of extensive long-term evaluations of compressive resistance, water absorption, fire hazard, environmental impact, and other suitable tests, has demonstrated Geofoam's outstanding performance, processability, and safety. Let's introduce the principal applications for the EPS construction method. At this construction site, where a retaining wall for the Namiki Bridge is positioned between an existing culvert and rail track, there was a concern that the load between the wall and the culvert would be too great using conventional fill techniques. The EPS construction method was utilized to reduce the load on both areas. There have been many inquiries from abroad about the EPS construction method, and study groups like this one from China are visiting Japan, learning about geofoam construction technology. In the Nakagawa Clover Bridge retaining wall project, EPS Geofoam was utilized because of its unique ability to absorb lateral pressure. Since no earth pressure could be transmitted to the river dike, construction had to be carried out within limited space on a very tight time schedule. The Kasi Nagisa Bridge is an incline bridge, connecting the Kasi Beach and the seaside park. The abutment backing of the bridge required about 15 feet of ground fill. There was concern that the weight of conventional sand fill would cause ground settlement and negatively affect the structure. Therefore, the EPS construction method was employed because of its lightweight characteristics, rapid construction time, and overall project savings. For a similar reason, the EPS construction method has been used in connecting bridges, abutment backing, and filling for the waste disposal treatment sites at Tokyo Bay landfills. On this project, the top 20 inches of fill is extruded EPS foam material, and the balance is molded EPS. The combination of geofoam fills provided both very lightweight material along with very high compressive resistance in response to the anticipated load. At this location, the EPS construction method is employed to counteract the concerns regarding settlement due to ground consolidation from the accumulation of about 40 feet of alluvial clay. Also, since temporary roads are positioned between bridge piers, there is a danger of negative friction developing at the base pilings. Geofoam is utilized to counteract and reduce this problem. This district has weak ground, consisting of a surface layer of 15 to 20 feet of viscous soil, humus, and a layer of sand. Of the 1,000 feet of road extension, 300 feet of the middle section used geofoam lightweight fill as insurance against settlement. As you can see, a difference in grade developed between the EPS banking and the other bankings. Since this road was built for temporary use, it was removed after about 4 years. At the time of removal, a study was conducted on the foam to determine if there was any deterioration in the EPS blocks. Testing showed that the performance properties of the material had not changed since installation, and no deterioration had occurred over the 4-year period. There was discoloration of the blocks due to subterranean water. In the expansion and improvement project at this two-lane highway, engineers had to contend with steep topography and continuous sharp curves. The site was evaluated and was considered to be too difficult and expensive for conventional construction methods. Geofoam EPS was utilized to minimize traffic congestion during construction, speeding the actual construction time and eliminating the need for large construction equipment. In this construction project to improve the Kendo-Yamakito-Fujino highway that passes through a very mountainous region, it was impossible to stop traffic altogether. Large construction equipment could not be used due to the location and condition of the site. In order to finish the project in the shortest possible time and to overcome the difficult conditions, lightweight geofoam EPS was employed, making it possible to build a 40-foot high retaining wall on the steep sloping land to support the highway. This area has a typical landslide topography, with terrace fields extending from the foot of the mountains to the seashore. Here, the EPS construction method was used as a means to reduce load. The EPS construction method will hold up in a landslide area even in an earthquake. Two large earthquakes occurred in 1993, one off the coast of Kushiro and another off the coast of the Noto Peninsula. At that time, there was concern about collapse and fire at EPS ground fill projects. However, no damage or problems occurred at either site. The Kasi-Nagisa Bridge and the adjacent seaside marine park are constructed almost entirely on weak ground, about 30 feet thick. Here, the EPS construction method was employed to create hills within the marine park, and there has been no effects of lateral flow on the base pilings of adjacent large buildings. The Suru Imperial Gift Park and Kiba Park area is situated on weak ground formed from an alluvial layer. The EPS construction method was used as a countermeasure against settlement due to ground consolidation. In this situation, lightweight EPS block fill positioned on weak soil was utilized to construct artificial landscape and to create a scenic area. On top of the EPS, covering soil was provided for the various trees, shrubbery, and flowers to make the park attractive. At the JR Hajima railway station, an expanded platform was built on the main line using geofoam. A new neighboring track was constructed, and then a new expanded platform was built in a 4-hour period after the last train and before the first train the following morning. The expansion project was part of the measures to ease congestion at the station, and the EPS construction method was employed since it allowed for the platform to be constructed in the shortest possible time without disrupting service. Here, the EPS construction method makes use of the lightweight, compressive resistance and handling ease of EPS foam to form a falling rock cover. Additionally, geofoam is used in a variety of other applications, such as underground pipes, retaining walls, buildings, and parking lots. The new expanded polystyrene construction method, born in Norway, extensively used in Japan, and is developing rapidly throughout the rest of the world. Geofoam provides engineered solutions for problems associated with weak ground and for lightweight fill, where traditional materials may not be suitable. The EPS construction method has significant advantages over conventional construction materials in time and cost savings, and this technology will